Hello and welcome to Introduction to Geology, where we're talking about the Earth system, geology as a science. In this module, we're going to be talking about components of the Earth system and geologic time. I'm Dr. William Patterson, and you're not. The climate system is driven by interactions between the atmosphere, the hydrosphere, the biosphere, the cryosphere, and the lithosphere. Starting with the atmosphere, this is a thin gaseous envelope that surrounds the Earth up to an altitude of about 100 kilometers. You can think of it as kind of a wet paper towel wrapped around a bowling ball in terms of its thickness. The cryosphere consists of the polar ice sheets, all alpine glaciers, and other surface ice and snow. The hydrosphere consists of surface waters that make up the oceans, lakes, rivers, and groundwaters of the continents. The biosphere consists of all organic matter related to life at or near the Earth's surface. And the geosystem is energized by solar radiation. The climate system is directly tied to what's going on in outer space, mostly the sun. The plate tectonic system relates interactions between the lithosphere, the asthenosphere, which we'll learn about in a few modules, and the deep mantle. The lithosphere consists of the strong, rocky, crispy outer shell of the solid Earth that comprises the crust and uppermost mantle to an average depth of about 100 kilometers, forming the tectonic plates. So the lithosphere is about as thick as the atmosphere. The asthenosphere, asthene meaning weak or weak sphere, is a weak ductile layer of mantle beneath the lithosphere that deforms to accommodate the horizontal and vertical motions of plate tectonics, the movements of plates. The deep mantle is the mantle below the asthenosphere, extending from about 400 kilometers depth to the core mantle boundary at about 2,900 kilometers depth. These geosystems are in turn energized by the Earth's internal heat. Now this brings us to the geodynamo system. This is the interactions between the inner and outer cores. The inner core consists of a sphere composed primarily of solid iron, extending from about 5,150 kilometers depth to the Earth's center at around 6,370 kilometers depth. The outer core is a liquid shell composed primarily of molten iron, extending from a depth of about 2,900 kilometers to 5,150 kilometers. So where's all this heat coming from? Albert Einstein, of course, derived the world's most famous equation, other than 1 + 1 = 2. In Einstein's equation, E = mc squared, we calculate the conversion of matter into energy. The E symbolizes energy, M, mass, and C is the speed of light. The speed of light is like really fast, so it's a big number, a huge number. A considerable implication of this equation is that a tiny amount of matter multiplied by a very large number is equal to another very large number that is a lot of energy. Splitting a small ball of uranium or plutonium atoms results in a bunch of daughter products and a small loss of total mass that releases an enormous blast of energy in such reactions. Radioactive decay, also known as nuclear decay or radioactivity, is a random process by which an unstable atomic nucleus loses mass and or energy by emission of radiation or particles. In this case, the nuclear weak force allows for the decay of a proton into particles and heat energy. There are many modes of radioactive decay, but some of them are very important for life on Earth. This is alpha decay of thorium-232. The decay heat of uranium and thorium, along with their daughter products, contribute to the heating of Earth's core. Together with potassium-40, in the Earth's mantle, these elements are the primary source of heat that keeps the Earth's core liquid and keeps plate tectonics moving. Here we see the basic history of the development of atomic weapons. The bomb dropped on Hiroshima was a 15-kiloton weapon, whereas the Castle Bravo, another American weapon, was tested in the Pacific to be 15 megatons, 1,000 times more powerful than the Hiroshima weapon. The B-41 bomb comes in at 25 megatons. One thing we learned from the Castle Bravo test in the Pacific was that lithium can play a role in generating much, much more power in an atomic weapon. And in fact, by the time the Tsar Bomba was developed by the Russians, based on information stolen from the Americans, they set off this 50 megaton bomb. This Tsar Bomba could have been much, much larger, vastly larger in fact. In reality, we can make an atomic bomb that can pretty much wipe out life on Earth, a single weapon. Now that we know this, and thanks to the Russian scientist Andrei Sakharov, who developed this weapon, knowing the capability, he toned it way down. But why? Why did he tone this weapon down? He realized that the weapon as originally designed would have blasted radioactive material well into the stratosphere, where it would circle the Earth, depositing radioactive material over the entire planet for many decades, perhaps centuries. So he toned it down considerably from what it could have been, and the result was the Russian government watched him every minute for the rest of his life. Spasiba, Andrei Sakharov, for keeping the world less radioactive. Ultimately, it was a show of force demonstrating Soviet nuclear capability, but was considered too impractical for military use due to its size, weighed 27,000 kilograms, and its destructive capacity. It does too much damage. So again, spasiba большое, Andrei. Back to business now. Natural radioactive decay is adding heat to the base of the plate tectonic system. But what's in it for us? What happens when we add heat to the pot? When we add heat to the bottom of a plastic or liquid substance, it results in convection. The warmer material is going to be less dense relative to the cooler material, and therefore it's going to rise. So we have the same thing happening in Earth. The spreading center, we have heat from within the Earth causing a decrease in density that forces material to rise. As it rises and spreads out, it drags material along with it. It grabs onto this material, in this case plates, tectonic plates, and pushes them away from the spreading center. This is where new crust forms. Now the convection grabs onto this new crust and drags it along with the other crust. But because this new crust hasn't undergone the same chemical distillation the continents have, it's going to be more dense than the continents. So it's going to ride underneath and disappear down subduction zones. So the convection generated by heat is going to drag plates away. As it drags plates away, it is going to force subduction because it can't create more surface area on the Earth. Accommodation space that's created here is removed in other places on the Earth's surface. The implications of this heat and convection for us is the geodynamo system. The relatively rapid motion of the liquid outer core stirs up electrical flow in the solid inner core, causing the Earth's magnetic field. This works a lot like a bar magnet. Given that context, we can now simulate the geodynamo in its most simple way by looking at how a bar magnet and the magnetic fields generated from that bar magnet relate to the North Pole and the South Pole of that magnet and of the Earth. You'll notice that the field lines originating from one portion of the magnet move away from the magnet and then return to the magnet in a different location. We can simulate that electromagnetically by wrapping a copper wire around an iron rod or a nail and connecting that wire to a battery. The electrical charge flowing through this wire moving along the rod is going to generate an electric field, in this example, an electromagnetic field. Now, the Earth is doing this naturally, and it's the rotation of the mantle relative to the liquid outer core, relative to the solid inner core, that's serving as a generator of the charge, kind of like the way an induction stove surface works, if you have one of those. When we look at the orientation of the magnetic pole relative to the geographic pole, we'll see that there's an offset. The geographic North Pole is the rotational axis of the Earth, while the magnetic pole is where the magnetic field lines re-enter the Earth. The North Magnetic Pole actually migrates all over the high Arctic these days, and it has throughout Earth history. Occasionally it flips over, and we have what's called a magnetic reversal. That phenomenon turns out to be very important and potentially fatal to us at some point in the geologic future. Maybe soon, maybe a long time off. When we talk about the Earth as an open system, what we're referring to is that it's not an isolated, sealed snow globe like The Simpsons. We're actually connected to the environment around the Earth. Those connections include the sun. The sun drives the Earth's external heat engine by supplying electromagnetic radiation to the surface of the Earth and to the outer surface of the atmosphere. Solar energy is responsible for driving our climate. As a result, this incoming radiation is going to warm the atmosphere to differing amounts in the different layers of the atmosphere. Radiation that makes it through the atmosphere all the way to the Earth's surface is going to bounce back as black body radiation. We'll talk about that later in the course. That in turn is going to heat the lower atmosphere, and this is what generates weather on the planet Earth. We heat the bottom of the atmosphere, and that makes it unstable. The internal engine, on the other hand, is powered by trapped heat. Internal heat, as we had just discussed, is generated within the Earth from the radioactive decay of certain elements at specific rates that we call half-lives. The heat radiating from the Earth has to balance the solar input and the heat from the interior. If this is not balanced between gains and losses, the Earth is going to get warmer or cooler. This interplay has been going on since the origin of the Earth and its atmosphere somewhere around 3.8 to 4 billion years ago. Meteors move mass from the cosmos to the Earth such that the Earth is currently gaining weight as it accumulates more dust debris and heavy material from space. However, simultaneously the Earth is losing atmosphere, constantly bleeding away predominantly hydrogen, but also heavier atmospheric molecules as well. And this has been going on since the beginning of Earth history. Speaking of Earth history, let's talk for a few minutes about geologic time. Geologists break the geologic history of the Earth up into components, just like a 9-season Netflix series with 15 episodes per season. We do this to better understand and relate our findings to other scientists. And remember, geology has a lot of time to deal with, so we've got a lot of episodes and a lot of seasons to consider, and that can all get confusing unless we put it in order. When geologists talk about the Cretaceous, for example, we all know instantly that it's a specific period of time in the Earth's existence. We initially divided geologic time up based on fossils that appear and disappear in the rock record. Later, we added chemistry that appears and or disappears, including isotope chemistry, and a number of other different lines of evidence that can be used to break the Earth's history up into time components. Now, starting with the earliest Earth history, 4.6 billion years ago when our solar system formed, the solar system consisted of a dust cloud that began rotating. As this rotation increased, the dust coalesced into planetesimals and ultimately planetoids and then planets. Back in the 1950s, Claire Patterson, pictured here, no relation, was given an easy assignment from his advisor: determine the age of the Earth. After a number of failed attempts where he got some weird numbers, Patterson realized that his lab was being contaminated by something. That contamination was from atmospheric lead coming from the burning of leaded gasoline. Tetraethyl lead was added to gas for decades to stop what's called engine knocking. Ultimately, he became the guy that stopped the lead from being put in gasoline. He determined the Earth was formed 4.55 billion years ago, give or take a few tens of millions of years. And now, after another 75 years or so of research, we've changed that from 4.55 billion years ago to 4.54 something billion years ago. At 4.51 billion years ago, the moon forms after a planet-like body, planetoid, crashed into the Earth and ripped off a big chunk of the mantle. This body was named Theia by Alex Halliday, one of my professors at the University of Michigan. As a result, our oldest lunar rocks are around 4.47 billion years old. The oldest continental rocks are found in Canada, in the Slave Province. These rocks were dated at about 4.03 billion years of age by Sam Bowring, one of my professors at Washington University. At 3.8 billion years ago, we see evidence of erosion by water and, perhaps coincidentally, the first signs of life. At 3.5 billion years ago, we see a record of the magnetic field. This means the geodynamo has initiated. And we also see fossils of primitive bacteria. At 2.7 billion years ago, we begin to see oxygen rising in the atmosphere. Now, this seems like it's positive for everybody and everything, but remember that the Earth was populated by anoxic organisms at this time. So oxygen is a poison to anoxic organisms. So suddenly the Earth poisoned itself at 2.7 billion years ago. At 2.5 billion years ago, our major phases of continental formation were completed. The origin of many of the continents today were in place. Those chunks, the Canadian Shield, for instance, the Brazil Shield, formed at this time. Moving ahead, we enter a cryogenic period. This is when the entire Earth is believed to have been covered with ice, or snowball Earth. We think this happened twice. After the recovery from this snowball Earth, we entered a period of great biological innovation. The Ediacaran fauna come along. As oxygen begins to rise, animals become larger because of this increased concentration of oxygen. And in the Ediacaran fauna, they become flatter, so they increase their surface area. Shortly after this Ediacaran explosion of life, we enter what's called the evolutionary Big Bang at 542 million years ago. This is believed to be the time when oxygen increased to levels that could support significantly larger organisms, and this is when all the modern phyla that we observe on Earth today first evolved. At 420 million years ago, the first land animals appear. And around this time, we have some large, strange, plant-like, fungus-like things appearing on Earth, occupying terrestrial environments. At 125 million years ago, we have the earliest flowering plants, angiosperms, and this is a major innovation, a major revolution in evolution. The sexual reproduction of organisms, in this case plants, leads to faster, more creative evolutionary advances. 5 million years ago, we have the beginnings of humans, primates that ultimately evolved into humans. And at about 200 to 400,000 years ago, we have the appearance of our species, Homo sapiens. Now, punctuated in all of this, including the cryogenic periods, snowball Earth periods, are mass extinctions. So snowball Earth obviously destroyed life. Those were mass extinctions. Subsequent to that, at the end of the Ordovician, the Hernantian extinction took place around 443 million years ago. That was a glacial episode that destroyed much of the life on Earth, the first true mass extinction. This is followed by other mass extinctions, including the Devonian mass extinction at 359 million years ago, and the Great Dying, the Permian mass extinction at around 251 million years ago, when almost all life on Earth perished. Around 95% of all species were wiped out at the end Permian extinction. But our ancestors survived. At 200 million years ago, a Triassic extinction. At 65 million years ago, we have the end of the Cretaceous extinction. It's now called the Cretaceous-Paleogene extinction. It was called the KT or Cretaceous Tertiary extinction until a few years ago.
This is the end, my